Yeah. Okay. Before I start today's class, I have to tell you that today would be the last day when you can drop this course. Last date for dropping the course. So this is just a announcement. I'm not asking you to drop the course. It's just to tell you that there is a last date that the institute gives, after which your course will be mentioned in your transcript. I also want to announce that the last week of December, we will have one more test, in-class test. In-class test. So I think December last week. So I'm mentioning this so that you will get prepared from now onwards. Today is December 14th. So December 14th. So that would be 2 weeks from now would be an ideal time. 2 weeks from now would be an ideal time. 21st and 28th. So maybe we will have it on 28th or 30th. The reason why I will announce the date later is because we are going to have a few days when we might have to miss class. So I will adjust the timing accordingly. I will try to complete as much as possible because this January 15th is the last day of classes. So let's now get going with today's topic. Today's topic is allyl complexes. These are complicated systems. I have indicated there are very complex structures that are present, and so it might be difficult sometimes, both in terms of chemistry and in terms of studying these things. But we will talk about synthesis and then the structures, both electronic and molecular structures, and then we will talk about reactions. These are fascinating complexes. There are as I mentioned, there are many different ways to make them. Here is one way to make them, and that is the treatment of a Grignard. The treatment of a Grignard. This is allyl magnesium bromide. So that is C3H5Mg I'm writing it in a very simple fashion like this, just to tell you that these are the components, not necessarily the structure of the molecule. But if I treat nickel dibromide with the allyl Grignard, I get a complex which has got two allyl species and one nickel atom. Two allyl species and one nickel atom. This complex is in fact quite fascinating. I will show you the structure in 3D. I think that would be the best. If I show you the structure in 3D, this is the structure in 3D. I hope you're able to see it. So there are two allyl moieties, C1, C2, C3, the 3 carbons, and another 3 carbons. So this is what one might call as a homoleptic complex. This is what is called a homoleptic allyl complex. There are only allyl ligands. There are two of them. And as you will notice, this is somewhat like this. So you have two allyl groups which are facing in opposite directions, and there is a nickel in the middle. It is actually what one might call a sandwich structure. This is, although very often people tend to draw it in this fashion, the structure is like this. It's a sandwich structure. So let me present to you one more possibility. This is a Grignard reagent, allyl magnesium bromide plus zirconium tetrachloride, and I have 4 allyl moieties now with zirconium. And zirconium is, I'm just looking at my periodic table, is in the 4D element, right? 4D element, and it has got 4 allyl moieties around it right now, and that's also a homoleptic allyl complex. I've not got the structure of this molecule, but this is pseudo tetrahedral, and they are all what one might call as eta 3 complexes. Eta 3 complexes because there are 3 carbons attached to the metal, and the 3 carbons are almost equidistant. If you remember the structure that you saw for nickel, you have I don't remember the exact distances, so I'll just quickly measure them. This is 2.026 angstroms, and the central carbon is 1.98 angstroms. So you have 1.98 and 2.01, 1.98 and 2.01. So this is 1.98. This is 2.01. So that's not what I want, and it's not going away. Moment. Just a second, I will restart it again. There you go. So actually, I intended to ask a question, and that question was given away. So these two reactions are a class of reactions which are labeled as transmetallation reactions. Okay, I intended to ask this as a question, but the question was given away in that when I made that mistake. So you're transferring the allyl group I'm transferring the allyl group from an electropositive element, magnesium, to less electropositive element, nickel. And because Br is better suited for the magnesium, you would end up with MgBr2 on this side, and this kind of a transfer of the allyl group from the electropositive element to the less electropositive element is favored, thermodynamically favored, and these reactions work very well. So transmetallation is probably one of the most popular routes to allyl complexes. So that is one thing that you can bear in mind. But there are many, many ways in which you can make allyl complexes. Here is another one. Here I am taking tetra-allyl tin, but this time the allyl group is in this fashion. So that's tetra-allyl tin. Okay, tetra-allyl tin plus palladium chloride. And this reaction is leading us to a very well characterized complex. This complex has got one chlorine, one triphenyl phosphine, and an allyl group. In fact, if you do not add this triphenyl phosphine, you would end up with a complex that is less easy to characterize, and that would be an allyl palladium chloride complex. That would be something like this, PDCl, and that is formed in solution, and that is a dimer. That's also known, and this complex has been transformed into this PPH3 monomer, which is well characterized. In fact, I think I have a crystal structure of that also readily available. This is the palladium chloride structure that I showed you just now, the synthesis of that, the triphenyl phosphine palladium chloride structure. You will notice that these are the allyl groups. C19, 20, and 21 are the allyl groups, and they're attached to the palladium in a very similar fashion to what we saw with the nickel case. So more or less, the allyl group is in a plane. Allyl group is in a plane, and the metal is like my fist here, and coordinated to the plane of the allyl group. But then the position of the metal is different in different complexes. In other words, if I use the two fingers in my left hand to indicate the allyl group, the thumb is one carbon and this finger is another carbon, then the position of my hand keeps changing from place to, depending on the metal, it moves a little bit. More or less, the central carbon is bonded to the metal. Very often, it is closer to the metal than the terminal carbons. And another point to note is that if I turn it around like this, I can see that my palladium atom is in between the three carbons. The palladium atom is in between the three carbons, but below the plane. Okay, below the plane in which the three carbons are present, but right in between. What that means in terms of bonding is something that we will examine in a little while. But first, let me explain to you the type of ways by which we can readily generate these allyl complexes. So I hope you are able to appreciate the allyl system. We will get back to the complexes that we have made. So what is this type of a reaction? What reaction would this be? What is this reaction? Any response? No response? Is anyone there or? Sorry?
We are there. Like, I think it's also transmetallation, but I'm not sure.
Okay.
Transmetallation.
Transmetallation, yeah. So this is also a transmetallation. It just so happened that this is a main group element. This is a main group element, and the main group element is transferring it to palladium. You'll notice that more than electronegativity, it is probably the net thermodynamics delta G of the reaction that makes a difference, because tin is now not so electropositive. No, it's not like the case of magnesium, where you had a very clear electronegativity difference. Here it is very clear that the palladium carbon bond is stronger than the tin carbon bond. Palladium is in a higher, lower down in the periodic table, and as I told you, the metal carbon bond becomes stronger as you go down the periodic table. So let's move on. Here is a different way of making allyl complex. Here I have sodium salt of manganese pentacarbonyl. Sodium salt of manganese pentacarbonyl. This is MnCO5 minus. MnCO5 minus, and this now makes an SN2 type of substitution on the tin. It forms a eta1 complex. Okay, this eta1 complex, allyl can in fact be in two avatars. One of them is eta1 and the other is eta3. Eta3 is what I stressed in the first part, but here is an example where you can distinctly see the eta1 species. So this is a distinct intermediate that upon standing or slight warming moves over by a loss of carbon monoxide. You end up with this eta3 species. The eta3 species has now got 4 carbon monoxides and eta3. So the manganese is actually a 7-coordinate complex. Coordination number is in fact a problematic count in organometallic chemistry, because as you noticed in the previous slides, the manganese would be sitting now somewhere here. So you can think of a virtual point here, and this virtual point is coordinated to the manganese. So although we look at it as a eta3 species, the coordination number of this species can be counted as 7. It can be counted as 5 also. But 7 is the one that we will be using. One can think of it as a pseudo 5 coordinate complex, but 7 is a better way to represent it, because we know very clearly that the bond distances between the carbon and the metal atoms are within the covalent bonding distances. Now, this reaction, the transformation of the eta1 to the eta3 species, is purely like an internal displacement reaction, where you have the olefin, which is a 2-electron donor, is replacing carbon monoxide, which is also a 2-electron donor. So it's this now becomes like chelating ligand, strongly held than the carbon monoxide. So that's the transformation. So how would you consider this reaction? What kind of a reaction is this?
So substitution reaction.
Substitution reaction, okay. Any other answers? So I introduced it as an SN2 type of attack, right? And a substitution reaction is something that plus Cl minus. That is an analogy with organic chemistry, and it's okay. Oops. So is there another way to look at it? So let's look at the oxidation state of manganese. Oxidation state of manganese is -1 in this side. It is +1 in this side. So you can think of this as an oxidative addition also. You can think of this reaction as an oxidative addition. Okay. So there are two ways to look at it. One is to look at it as if it's an SN2 substitution reaction. But as I told you, oxidative additions are very often SN2 type reactions where you have a change in the metal's formal oxidation state. Formal oxidation state change happens. Okay, let's keep going. Here is another example. Here also the first step is an oxidative addition. You have a cobalt complex which is +1. Cobalt complex which is +1. This is allyl iodide. So this is allyl iodide. And you will end up with a complex which is now, I think I have animation on this slide, so I might mess it up, but let's go ahead and write it anyways. Cobalt, carbonyl, and then an allyl group. So here is an example which is very similar to what I told you before. This is an eta-1 complex, and it is set up to do a substitution reaction of one of these ligands, because internally you have another eta-2 donor. Sorry, I should say a 2-electron donor. So this 2-electron donor now will do a substitution reaction. But before we proceed further, you will notice that this complex is in fact positively charged, plus I minus. Okay, it's got plus I minus here. So this is a example again of oxidative addition +1 to +3. Okay, let me see if the animation messes it up. No, it doesn't. So I can easily transform the eta-1 to an eta-3. It doesn't need further explanation. But the final complex that is isolated is surprisingly complex which doesn't have carbon monoxide. Carbon monoxide is kicked out by the iodine. This is something I cannot predict a priori. Whether this will happen or not is something that I cannot tell. But thermodynamics seems to have favored this reaction between this positively minus to be where I have lost the second carbon monoxide. So in this reaction, there are several steps which are happening. First step is an oxidative addition. Second step is an internal substitution. And a third step, which is also a substitution reaction. And in the substitution reaction, the second carbon monoxide is also lost from the coordination sphere of the cobalt. So here I have an interesting species. I have an eta-3, eta-5 set of ligands. We have not talked about the cyclopentadienyl. We'll talk about it a little later. But the allyl species is now bound to the cobalt in a eta-3 fashion, and that's the species that we are concentrating on. So we have looked at two different ways of making the allyl complex. One was a transmetallation, another was a reaction where you have oxidative addition and of course followed by substitution. A third method would be adding a formal hydride. species, okay, a metal hydride species. So here is HCOCO4. HCOCO4 is, as you know, it's only a proton. It's actually a good acid, but formally it is a hydride. So this is a reaction in which you can lose a carbon monoxide from the species. So HCOCO3 would be in equilibrium with this plus CO, and the diene can now interact with a cobalt in the free coordination site. So an intermediate for this would be HCO bond uncoordinated CO. And this species can undergo a migratory insertion reaction, right? And the insertion will take place in such a way that this will now give me allyl species. Okay, this will now give me an allyl species which has got soaps. I have not written that. Now give me this is the methyl group which is formed. These are the two hydrogens. Okay, it adds on in such a fashion that it gives me carbon cobalt bond, which quickly transforms into due to insertion of the hydrogen, migratory insertion of the hydrogen to give me a tris-carbonyl cobalt complex, which has got an allyl species attached to it. So here, what happens is there are two different ways by which the allyl group can interact with the cobalt. One is with the methyl group pointed away from the metal, and the other one is when it is inside. So both of them are possible. This is also possible, this is also possible. And in fact, a mixture of both are formed. Of course, one of them is going to be thermodynamically more favorable than the other. And you can intuitively understand that this would be a better species because the methyl group of this carbon is now going to interact with this hydrogen. Okay. I will probably have some allyl complexes which are posted for you in the files, so you can examine them in 3D at leisure. But right now, I will not bother about that. Okay, so this is, I said it is formation addition of a hydride, even though we know it is a proton, because the nature of the intermediate, we normally call this a hydride, so I'm calling it a hydride addition, but it's pretty much a proton addition. As far as electron count goes also, you end up with a cobalt in a positive, you think of it as if it is a allyl as a negative species. So, for example, here, when you do the electron count, you would, in the ionic method, cobalt is +1. Okay, so that's the reason why I'm saying that. Okay, so oxidative addition is in fact something that is carried out with the proton. In this example also, you have a manganese complex which is coordinated. These are carbonyls. CO, CO. Anytime you have metal with nothing attached to it, just like you have methyl groups in organic chemistry, in organometallic chemistry, you have carbonyls. So you have a manganese carbonyl compound with an allyl complex, which is eta 2. This eta 2 complex, if it is protonated with HBF4, the proton ends up here and leaves as H2O. So you end up with an allyl complex, which is again eta 3 and eta 5. But notice that you have in fact moved from manganese 1 to manganese 3, +1 oxidation state to +3 oxidation state. So here is another example where you add a proton. This time you add the proton not to the ligand, sorry, not to the oxygen, but to the carbon directly, and you end up with, this is 2,3-dimethylbutadiene, 2,3-dimethylbutadiene coordinated to iridium 1. Addition of hydrogen to one of these places, H plus addition, results in the formation of allyl complex, which is now eta 3, and the reason it adds on to one of these terminal methylene groups is because it forms a nice allyl complex, which now is again +3 in oxidation state. You need carbon monoxide to fulfill the vacant coordination site, otherwise it will be coordinatively unsaturated. Coordinatively unsaturated. And so it requires this carbon monoxide. It could have been any other ligand plus L, and that will give you a stable complex, which is iridium 3 now, which is iridium 3, and it is having 4 plus 2, 6, 6 plus 6, 12, 12 plus 6, 18 electrons. So we have now covered 3 ways of making it. Either you look at it as a hydrogen addition, forget about the proton or the hydride. If that is confusing, let's take it as hydrogen addition. So you have oxidative addition, you have transmetallation, and now you have had one more addition of a proton. Okay, so here there is an unambiguous addition of a negatively charged species. This is a complex in which molybdenum is bound to butadiene. So it's a eta 4 complex, eta 4, and here it is eta 5. So you have 2 different carbon ligands, pi systems, which are coordinated to the molybdenum, and you're adding a negatively charged species, which is an anionic species, and you end up adding that anionic species to the terminal carbon of butadiene, and you end up with a eta 3 and a eta 5 complex. Now it's neutral. So here there is an unambiguous addition of an anion. And let's look at the oxidation state of molybdenum. This is molybdenum +2 here, and it's molybdenum +2 here. No change in the oxidation state. no change in the oxidation state of molybdenum. You might ask the question, why is this R minus attacking? You really have multiple choices. The R minus could have attacked the butadiene, it could have attacked carbon monoxide, it could have attacked the benzene ring. Of course, you would say that because it's negatively charged, it may not attack the Cp minus. So there are three different places where the R minus can attack: the diene and the benzene. Why not? So these are some interesting features of nucleophilic addition to coordinated ligands. We will talk about them in a subsequent lecture and explain them using frontier molecular theory. Okay, we'll do that a little later because it requires a lengthy discussion on how these things are working, but it's an interesting question. But right now, let me limit myself to the synthesis of these complexes. You have an allyl complex formation using the addition of an R minus to a diene. Okay. One more method. As I told you in the beginning of the lecture, there are several different ways by which you can make allyl complexes. And this is probably the only ligand in which there are a multitude of ways by which you can reach the same destination, which is eta-3 allyl species. A lot more than other ligands. So here is a species in which there is a nickel phosphine where the phosphorus ligand is actually trifluorophosphine. And as I told you, or I think I told you, trifluorophosphine is almost as good as carbon monoxide in terms of stabilizing zero oxidation states. So I have the substitution reaction now. PF3 has left in favor of an eta-2 alkene complex. That's what you form in the first instance. Now you have the metal sees 3 hydrogens in an adjacent carbon. So it's difficult to label this as beta carbon, but it is in fact a beta position. Beta carbon has 3 hydrogens. And one of these hydrogens, just like you have a migratory insertion to a coordinated species in the beta position. So now, if I count it like this, this would be actually gamma, beta, gamma. Let's make it gamma. So you have, that's the gamma carbon has got 3 hydrogens. And one of these hydrogens can do a migratory insertion to give you an eta-3 allyl complex. Now, of course, the nickel has got 2 anionic ligands. So this is in +2 oxidation state. So you can think of it as an oxidative addition. Of an allylic CH bond. Oxidative addition of an allylic CH bond. You can think of it like a migratory insertion reaction into the gamma position. Okay, so I have written it like this, but this complex is in fact thermodynamically very close to the olefin complex, and it seems to be in equilibrium at -50, -40 degrees centigrade. You can push the reaction to either direction. Slightly higher temperatures, this is more accessible. So which means it's thermodynamically less stable. This is the thermodynamically stable form of the product. So let's see whether yes. So this is a reaction which can also be called oxidative addition, but I have labeled this as a migratory insertion reaction, but it's not a beta migration, it's a gamma migration. Okay, one more example like this where a gamma hydrogen in a olefin complex can be abstracted by the metal. This case is palladium, and the palladium is in +2 oxidation state, and you'll notice that at the end of this reaction you will have no oxidation state change in the case of palladium. In the previous instance there was a very clear oxidation state change. In this case there is no oxidation state change. So how does this happen? Here is the steps of the reaction written in detail. If you take this, which tetrachloropalladate sodium, tetrachloropalladate sodium is an excellent starting material for a variety of organometallic compounds. The first step could be a substitution reaction. Notice that PdCl4 is 2-, so it is palladium in +2 oxidation state. One of the chlorines is leaving, so that's indicated here. So you end up with a uni-negative complex +Cl-, and this complex now can do oxidative addition of the palladium, and so that's what they have written here. So the books prefer this mechanism where you have a hydrogen transferred to the palladium and the Cl- leaving, which results in an oxidation state change of +2. This intermediate is never isolated. This is just hypothesized as shown in books, but I will just show you in a minute that this is not necessary. In this particular step, in this step, these two, it is just palladium 2. We are still having it as palladium 2. This is the oxidative addition step, and you have now a palladium +4 being formed as a result of Cl- elimination. If you eliminate Cl-, then you end up with this species. If you usually in these reactions you use triethylamine as an acid sponge, and you end up with this palladium dichloride complex. As I told you, this complex I introduced it to you earlier as a dimer. I just wrote it as a dimer. This was one of the first complexes that was formed. It was made as early as 1959. This complex was known as early as 1959. And is the first allyl complex that was ever synthesized. And this triethylamine hydrochloride is what is precipitated. It drives the reaction in this direction. But notice that this is never isolated. It has never isolated. So just to explain the reaction, the books give this mechanism. But I actually prefer a different mechanism. I feel that this is a better alternative to understand this reaction. And that is, first, of course, is a substitution reaction. This is a substitution reaction. In the substitution reaction, you can think of this hydrogen leaving as H+. Leaving as H+, and this Cl- going as Cl-. Okay, so you have removed H+ and Cl- from the system, and so the net charge on the complex, remember, you have a negative charge here, you have a negative charge here. You have to keep the charge because you have removed a neutral HCl from the system, and you end up with palladium in +2 oxidation state. There is no need to do an oxidative addition here. You can lose an H+ and a Cl-, and this HCl can be removed with Et3N as Et3N hydrochloride. Okay, so this is a species which can now lose a chloride and form the diamond. Now, although I've written it like this because it's very difficult to draw the other structure, but it is likely, not likely, it is existing in this type of dimer. That is more difficult to write. Here you go. Okay. I hope you are able to follow this structure where you have the palladium chloride dimer in the middle, and you have one allyl eta 3 in the top, another eta 3 in the bottom, and you have a nice sandwich type of structure with a big filling in the middle, which is formed by this palladium chloride. So you can think of this like a sandwich where you have two allyl groups on either side. Okay. So this is just both of, my mechanism is also hand waving. What the books give is also hand waving because neither of us know the intermediate that is involved, but I prefer a reaction in which there is no oxidation state change, because palladium, platinum are known in +4 oxidation state, but then they have different type of ligands, very electron rich type of ligands. Here, it's just a hypothesis that this is not needed. So one more type of reaction. Here, this is a bit esoteric. You have nickelocene. Nickelocene is a 20 electron complex. It is not very stable. It's not very stable because it's got this extra 2 electrons in anti-bonding orbitals. So this is not a stable system, and it is probably, not probably, it is in, you can think of it as an equilibrium between a species in which nickel is coordinated to eta 5 on one side, eta 3 on one side, and so these type of species would be fluxional, and you have an isolated double bond. So this double bond can be reduced with sodium and ethanol. Sodium and ethanol is a reducing agent which reduces this isolated double bond, resulting in a eta 3, eta 5 complex, okay, which is now an 18 electron complex. This is a unique example. It's not a generalized, not a general method, but this is one way in which you can make another eta 3 allyl complex. So here is yet another method, but these are methods which we have already encountered. In this instance, palladium, this palladium is in fact negatively, it's an electron-rich system. So you can think of this as a substitution reaction, which leads to the allyl palladium chloride complex. This reaction, in fact, requires a carbon monoxide atmosphere or SnCl2. SnCl2 will be oxidized to SnCl4 in the reaction medium, and it's also known that in the presence of carbon monoxide and in the presence of tin chloride, palladium chloride is reduced to palladium 0. So this is a reaction where palladium can go to palladium 0 and subsequently can oxidatively add the allyl chloride to give you the palladium allyl chloride complex. So these are oxidative additions to palladium 0. Now, one other esoteric method of making it is to use palladium 0 as metal vapor synthesis. Metal vapor synthesis is a kind of is a white elephant now. Not many people use it, but in some cases you may not have an option but to use metal vapor synthesis because because that would be the only way in which you can get a pure compound. So here is an example where you have a benzyl chloride, CH2Cl, and you are making a eta-3 complex using 2 carbons from the benzene ring and 1 of the benzylic position. So this is the eta-3 complex. All right. But then you have destroyed the aromaticity of this ring. The aromaticity of this ring has gone for a toss, and you have an eta-3 complex being formed. So these are, like I said, in order to force this ring system to form an eta-3 complex, you can in fact use metal vapor, because then the ligand, the metal doesn't have much choice other than to do an oxidative addition and to force the benzylic system to become a eta-3 complex. Okay, so the 3-dimensional structure of the allyl complexes is something that I have already shown you. I have several other structures which I will load in the website, loaded in Teams website. Not yet, I will do it right now because I have already shown you 2, and I think I showed you this complex, and I think it's better that you do it yourself in order to appreciate the complex. Let's now look at the bonding. What I have for you here is the allyl cation. So this is allyl cation, and I have 3 of the, because it's an allyl cation, if you think of the allyl species as a radical, then of course there will be 1 electron in this molecular orbital. Okay, now I can show this for you in 3D, and I will show that to you in 3D. That is probably better. One moment. Yeah. So I'm going to show this for you in 3D. This is the allyl molecular orbital. I hope you are able to see the allylic species. I'm kind of rotating it with my mouse. I will make these molecular orbitals available for all of you to view and visualize. I will give you the website address shortly. So you will be able to see these molecular orbitals for yourself, manipulate them. There are a variety of ways by which you can manipulate it. This is a magnifying glass. I think view is, yeah, you can manipulate it like this and rotate it using the top the top arrow. So I'm just showing you these. This is the HOMO. This is the HOMO. This is the highest occupied molecular orbital. As far as the fragment interacting with the metal complex, it is this orbital which is going to donate electron density. Remember, we are going to think of it as an allyl anion. If it's an allyl anion, it is this orbital which is going to be occupied with 2 electrons. I hope you are able to follow. The reason why I have not done the allyl anion calculation is because if I do it as an allyl anion, the anionic species will be occupied, but there will be some distortion. So I decided to do the allyl cation, but I will do the anion also and show it to you. Now, this species, this is also going to be occupied, and this is going to be unoccupied. Okay, so this is going to be unoccupied. Remember what I told you about the metal is present in a plane which is below this plane. Right now, I am rotating it in the plane perpendicular to the screen, and the 3 carbons are in a single plane. Let me go back to the screen where I have the 3 orbitals. In the allyl anion, this would also be occupied. Now we can match the metal orbitals. We can match the metal orbitals with the allyl species. This is definitely empty. Okay, this is definitely empty. And if you remember what we have studied so far, the s and the p orbitals are empty. In a 3D, 4D, 5D element series, s and the p are definitely empty. Whether these d orbitals are empty or filled depends on that metal system. So, but let us assume that because it forms a complex, that one of them at least is available for accepting electron density, 1 or 2 of them are available for accepting electron density, in which case it would be a mixture of S and dz squared. But if I have the metal sitting below the allylic plane, then you can imagine the dz squared being the most suitable. So I'm having this pen, I'm holding this pen on my fist so that the dz squared is now pointed towards the allyl group. So if I put it like this, then all 3 carbon atoms are having the same phase, and they're having this p lobe, which is in the same phase, all 3 carbon atoms, right? All 3 carbon atoms having the same. Let me use a color which is not there in this, so that's not very visible. Use black. So this lobe, which is below the allylic plane, is going to interact with my metal, and my metal has got an empty orbital and a combination of either a pz, the pz orbital, or the dz squared orbital and the s orbital can all interact with this combination. So this is capable of interacting with s, dz squared, and pz. All of them can interact. So assuming that this is the z-axis and the allyl group is sitting somewhere like this. Okay, the allyl group is sitting somewhere like this. Now, the metal can also accept electron density through another orbital. If it is also empty, then it can also accept another pair of electrons from the allyl group, in which case this will also be filled. Allyl anion, then this is, these 2 are filled. this is empty. Okay, if it is an allyl anion. Then I will end up with a d orbital which has pointed towards with the allyl in this orientation. If I have any orbital which has got two lobes pointed towards it with opposite signs, that means it has to be, if it is along the x-axis, it will have to be a dxz orbital. So the dxz orbital can interact with this. So I need this to be empty, this to be empty. And then I can have a 4-electron donor, which is donating a pair of electrons to the metal. 2 pairs of electrons to the metal, one from this and one from this. 2 electrons from here also. And then back donation can be done from the dyz. And to imagine that, you need to go back to my orbital picture and see this. This is my psi 3. This is my psi 3, which will look like this as far as the metal is concerned. So if I have one lobe here and one lobe here, one lobe here and one lobe here, the metal can be somewhere in the middle. Then I can have good overlap with this set of orbitals. Okay, so that is what I have to indicate in this picture. So if this is dxz, then this will be dyz. If this is dxz, then this will be dyz. It can also be, this can be px, this can be py. Px can also accept, but px will have lateral overlap. Okay, px will have lateral overlap, and the y will have the d will have oriented orbital, so it will have better overlap. I will continue with this. I noticed that the time is up, so we will stop here and continue with the bonding description in the next class, and we'll also talk about some reactions. So, any questions?
So can you explain that dyz once more, how it is?
I will do that in the next class, definitely. Okay. So anything else? Sorry. One of you have a question? Okay, you can type it in the chat box if you find it difficult to speak because you have some other competing noise. Otherwise, I will stop the recording here. And we'll continue in the next class.